I just realized like a hot second ago that we never actually finished the last example from the notes from last time. I like put the answers in a thing up on Blackboard, but we'll go through that really quick after I talk about this this final exam hoopla in a second. So also, if you have a topic that you want to go over for the rest of class once we finish our notes, let me know in chat. Otherwise, I have a couple things prepared. But anyway, your final is on Thursday, not 2 days from now. Next at 12:30 p.m. So note the slight time difference. The exam's going to be on Blackboard, where they usually are. So if you've never taken one of my assessments on Blackboard, it's under the assignment tab. I'll post like a mock exam, probably just made up of a bunch of old quiz questions just to save myself time. Just so you can get a feel for like the layout of it. But if you've taken, any of the quizzes or anything like that on Blackboard, it'll be pretty similar. I haven't written it yet, but it's most likely going to consist of mostly short answer, multiple choice, true false types questions, things that are quick to grade and hopefully Blackboard can grade correctly because the turnaround for getting these grades out is quick. So I want to make sure that I can grade them quickly. There probably will be some, slightly longer free response questions, but it'll probably be the vast majority of them being shorter answer type questions. In terms of things like proofs, I don't think I'm going to ask you to prove anything from scratch. What I might do, again, I haven't written the exam yet, but I have a couple ideas. The ideas I'm playing around with is I might have you like fill out a proof with, just a couple blanks, like some of your homework was for proof sections. I'm also thinking about providing a proof with errors, and then you have to figure out where the error is. I'm kind of playing between those two. But anyway, so I don't think I'll ask you to prove anything from scratch because they'll just take too long and those will be terrible to try to type into Blackboard and all that jazz. So that's the thing. The exam is going to be open note, open resource. So essentially you can use anything that is already at your disposal, lecture notes, video recordings, anything you can already find on Google. So let me be sure to clarify that that does not mean that you can post things online to get help from internet strangers. So no Chegg, no Reddit, no Stack Exchange, no whatever. But anything that's already online, already Googleable, that's a word, is completely fair game. The exam period is 2.5 hours. I try to write approximately an hour and 45-minute exam, so just a little bit longer than the exams you're used to in class. Anyone who has documented time, which I don't think there's many of you, but there's at least one. But anyway, those of you who have documented extra time will receive it automatically. Well, not automatically, I have to set it up through Blackboard. So if you click on it and you should have extra time, but it still says 2.5 hours, close it immediately and let me know. During that 2.5 block of time from 12:30 to 3, I will be here in this Microsoft Team meeting. You do not have to be here, but I'll just be, sitting around, bored to tears. If you have any questions, you feel free to pop in and ask them. Otherwise, I'll be checking my email pretty frequently. And then the last thing I want to say is I'll have office hours this week. Well, one time this week and then one time next week. On Thursday from 1:30 to 3:30 and then Tuesday from 11 to 1. I know that's like kind of somewhat in the middle of finals if you have finals on Tuesday. I tried to make it in like the slightly in between time. But anyway, those are going to be in my office hours team, which if you haven't already been brought into it, code that I just highlighted down at the bottom to get in there. So you essentially just go on Teams, go to the Team tab, and it says there's like a join thing in the right corner, and you click on that. I'll post the office hour stuff to Blackboard in case you need it later. But that's where I'll be because remember today's the last official meeting that we have. All right, I think that's everything I wanted to babble about. So, as I mentioned, I forgot that we haven't finished this. I knew there was one class and I couldn't remember which one it was, and it's you guys. And that's because we kind of had to go back through that other one again, which was perfectly fine. So let's go through this last example of expected value really quick. So remember, we were talking about probability essentially in 4-4. And then this last piece of 4-4 was the expected value, where essentially you have a sum of the value that you can get times the probability that you can get that value. And so we looked at this really, this one about the lottery. But now we have this one where we have a natural number n is chosen at random from the set of the numbers 1 through 135. Let d be the number of digits that n has, and what is the expected value of d. So essentially we have to find what are the possible number of digits, and then what is the probability of getting that number of digits. So you essentially have three possible numbers of digits. So the possible, that's not right. The possible number of digits. So you can either have a 1-digit number, a 2-digit number, or a 3-digit number. Those are like your choices. So now we have to figure out essentially the probability of getting that many digits. So let's look at, well, first off, we have a total number of 135 numbers, right? 135 numbers between 1 and 135. So to find the probability of getting a certain number of digits, we just need to find out the amount of numbers with that digit and then find that ratio. So let's look at 1-digit numbers first. So if we think about the 1-digit numbers here, well, that's going to be 1, 2, all the way up to 9. So there's essentially 9 of those. So there's 9 numbers that have 1 digit. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them. So essentially the probability of the number of digits being 1. So remember we have like this kind of odd notation that has too many x's floating around. But here, since we're naming the variable d, we're going to use d instead of x's. So we're saying the probability that the number of digits is 1. Well, there's 9 numbers that have 1 digit out of 135. So we would have 0.06667. Let's take a bunch of decimal places. Remember when we're talking about a probability in general, you would change this over to a decimal. A percent. You would change this over to a percent for your final answer. But since we're using the expected, we want the expected value. The expected value uses the decimal, so I'm not going to worry about changing this over to a percent. So now we've got to look at 2-digit numbers. So for 2-digit numbers, that's our 10, 11, 12, all the way up through 99. That's like the bulk of the numbers that are in there, right? So if we count up the numbers from 10 to 99, that's going to give us 90 numbers. So essentially 11 to 99 gives us 89 numbers, and then the 10 is like the 90th number in a way, if that makes it easier to figure out how many there were. I was kind of racking my brain the other day when I was looking at this. It made me really sad that I couldn't figure out how many numbers there were between 10 and 99. So the probability that we have 2 digits here is we have 90 numbers that have 2 digits out of a possible 135 numbers. So the probability as a decimal of getting that would be 0.66667. Let's take the same amount of decimal places. And then, of course, we've got one more option, which is the 3-digit numbers. 3-digit numbers. So that'll be our 100, 101, all the way up to 135. So that'll be 36 numbers. And if you think about it, if you're having a hard time figuring out how many digits there are, if we add these up, you should get 135 because that's how many numbers we have. So if we add up 9, 90, and 36, we do get 135. So maybe we miscounted somewhere, but we didn't. But that's a good way to triple check that you probably got the right amount of numbers in each spot. So the probability that the amount of digits would be 3 is we have 36 out of 135. So 0.3 0.2667. So with expected value, you take essentially what's the word I want to use here? The actual value that you get from that, and then the probability of getting that value. So our possible values are 1, 2, or 3, and then the probabilities are what we just found. So the expected value for these number of digits, well, to get a 1-digit number, there was a 0.06667% chance. So the value of the number of digits is 1, and then the probability of getting that value is 0.06667. And then we add that, we have a option of the value being 2-digit number, and the probability of that was the 0.66667. Lots of sixes. And then we have to add that to just that last value. That last possible value is 3. And the probability of getting that value, 0.26667. Punch that sucker into a calculator. Get approximately 2.2. And so remember what this is actually telling us. Now, again, sometimes it has a meaning contextually, and sometimes it doesn't make logical sense. So this is essentially saying, on average, if you just chose a random number between 1 and 135, you could expect on average to pick a 2.2-digit number, which again is why I say that it has context, but sometimes it doesn't make logical sense. Like obviously there's no number that's 2.2 digits, but it's just kind of telling us that it's much more likely to get more towards a 2-digit number than it would to be getting a 3 or a 1-digit number. And since it's slightly higher than 2, there's probably a slightly higher probability, which there is because we found them all, of getting a 3-digit number than a 1-digit number. So even though saying getting a 2.2-digit number doesn't make any sense, this is just saying on average, if you just picked a bunch of numbers at random, on average, if you just took the number of digits and averaged them up, it would be approximately 2.2 digit. Does that make any sense? Probably not. Questions, concerns on that? So expected value, figure out the kind of options you have for your whatever you're finding. So since here we were talking about a number of digits, the number of digits had 3 choices, 1, 2, or 3. And then you find the probability of getting that choice. So say we were rolling a die and we wanted to figure out the expected value of rolling a die. Your options for a 6-sided die, 1, 2, 3, 4, 5, 6. You would find the probability of getting all of those rolls and add up the sum of the value times its probability. Questions, concerns about that? Okay. I'll wait like 5 more seconds in case people are writing something down. Then no one said any topics they want to go over, so you feel free to pop them in now. But otherwise we'll go over, I've compiled a short, well not that short, but I started compiling some review questions starting back from more chapter 1 material because it's been a long time since we covered that. The thing that I'm about to pull up isn't posted anywhere. So I'll pause every once in a while in case you're trying to write the questions down. And I'll post a blank, actually, well, it doesn't help you right now, but I'll post a blank copy and the filled out copy on Blackboard after class, because we might not get through all of it, but we'll see how far we get. We might get through all of it and then I have to think of more questions. Who knows? So I'll give you all a couple seconds in case you want to write this question down, or at least like the important parts of this question, which is really just this piece right here that I just drew a line through. So remember, your final is cumulative, so any material we covered is fair game. So a lot of this material that I have here is, again, back from stuff we did more towards the beginning of the semester to remind us of what the heck all this is. All right. So let's say we're looking at this problem. So we're letting P represent Jamie is 20 years old, Q being Jamie lives alone, and R being Jamie has a cat. So say we wanted to translate the following sentence to formal logic. If Jamie lives alone and is not 20 years old, then she has a cat. So we essentially want to take this sentence and turn it into letters and symbols. So what do we have here? We have Jamie lives alone, which was Q. We have an and, which, goodness, why is my brain forgetting which way an and goes? Ands go this way. So an and, remember, we have our and, our or, our implies. We have an exclusive or that we don't use a lot. That's the one where it's one or the other, but not both. I feel like I'm missing something. We're missing not. I think that's it. Anyway, so we have Jamie lives alone and is not, so not 20 years old. Jamie is 20 years old was a P value. And then we have the then. So remember, whenever we're translating these, if you have an if then, that's what gives you the implies, but the symbol essentially goes with the then. So we have the implies there. She has a cat was R, so we end up with Q and not P implies R. Also remember that anything that comes before the then, if it's more than one symbol, maybe I should say more than one letter. How would I say that? Because if it was a not P by itself, then you wouldn't really need parentheses. But if it's got more than one letter in there, make sure to put anything before then in parentheses, or else it's technically not right. So be careful of that. And then what if we wanted to take something that isn't symbols and translate it into English? So remember, with these, we kind of have the kind of literal way and then the more modern English way. I'm probably going to want at least an attempt at modern English. Maybe it's not the best modern English I've heard in my life, but try to make it at least slightly modern English. But let's go with the literal for a second here. So if we have P or R, that would be 20 years old or has a cat. So Jamie is 20 years old or has a cat. And I'm going to fix something in a second. And then I come up to an implies. So that would be an if then. So I'm actually missing an if from the beginning. So I'll need to shove an if in the front. So if Jamie is 20 years old or has a cat, then not Q. So they don't live alone. So if we wanted to be literal, we would say something like, then it is not true that Jamie lives alone. Whoops. But I'm going to go ahead and kind of, again, put it in a bit more modern English and say something like, then she doesn't live alone. And that would be that sentence in at least decently modern English. If Jamie is 20 years old or has a cat, then she doesn't live alone. All right. So now we want to give the converse of P implies Q and then write it in English. So in symbols, remember that the converse is Q implies P. You essentially just flip it over. Remember, we have another thing called the contrapositive. This is like half review, half just doing problems, so I'm kind of doing a little bit of both here. So remember, when you have a contrapositive, you start with a P implies Q, and then you end up with not Q implies not P. So the converse just switches them, where the contrapositive essentially switches them and negates them. But anyway, going back to this problem, give the converse of P implies Q and write it in English. So in English, we'd have Jamie lives alone implies that Jamie is 20 years old. So phrasing that a bit better than the imply statement would be if Jamie lives alone, then what's P? Jamie's 20 years old. There's something in my way, sorry. You could, of course, say then she is 20 years old. You don't have to put Jamie again, but just something to get the point across. Questions, concerns so far? Cobwebs dusting off your brain? I didn't leave myself enough space for this next one, did I? I don't think I did. Oh well, here we go anyway. So truth tables, it's been a while since we've done one of those. So we don't really need the actual translations for this one. It's just part of this problem because I felt like it. So remember truth tables, that's where you have all your T's and F's for true and false. And since we have 3 letters here, we're gonna need 8 rows. So remember, it's always essentially 2 to the n rows, where n is the, I don't know, number of letters, I'll say. There's probably a better way to phrase that, but. So we essentially have, so I don't know, can I fit 8 rows in here? So we're gonna have P, Q, and R. I guess if I write kind of small, let me zoom in a little bit. That's not what I want. Zoom. There we go. So we have true, 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 true. Oh no. Let me try it one more time. P, Q. Shove it up there a little bit. True, 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 false, false, false. I shoved it in there. True, true, false, false, true, true, false, false. So there's like a million ways you can, not a million, but a bunch of different ways you can set this up. The way I personally like to do it is I like to make my P's just half and half are true, half are false. Like just the first half is true. And then if I have the next letter is essentially, if I have 3 letters, it's going to be 2 true, 2 false for the second one. So 2 true, 2 false, 2 true, 2 false. And then the third one is going to alternate. Each one being true and false. There's of course a bunch of different ways you could get that across, but as long as you get all of these situations in there, it doesn't really matter. Now also for your exam, when you do truth tables like this, I always want you to give me essentially all of the columns in as many pieces as necessary. I don't know how to phrase that very well. Essentially what I want is, I want to say when there's knots, please actually include those knots by themselves. So I know that you could just consider P and not Q as considering, you know, just negating Q in your head when you're working on it, but I want that negation to come up as its own column as well. So if we want to negate Q, that's essentially the one that just flip-flops it over to the other. So all of the trues are now going to become false, and all the falses are going to become true. And then we need to build up to the statement we actually want. So the next thing I would personally do, I don't know what else you would do, is I would do the P and not Q column. So remember, and they have to be both true. So remember, it's not that they both agree, it's that they both have to be true, because what we're actually looking for here is the truth of the statement. So if I say I went to the store and bought bread and eggs, but I come home with no bread or eggs, then it's not true that I went to the store and bought bread and eggs. So they both need to be true. So let me just help myself a little bit and highlight the 2 columns I'm looking at here. So we're looking at these 2 columns. So the first set is true, false. So that would be false. True, false, false. True, true would give true. True, true would give true. False, false would be false, because again, they both have to be true. And so essentially the rest of these turn out to be false. Ooh, can I erase this now? Oh, I did it. And then once you get there, now we can finally do our implication. Now remember, with implies, this is the one that gets a tiny bit weird. The only one that is false is when it's false implies true. So essentially, if I say something like, if it's raining, then I will give you a ride home. Sorry, I said that backwards. Sorry. Sorry. I didn't say that backwards. Sorry, my brain's exploding. The only one that's false is true implies false. I'm so sorry. Only false for implies is true implies false. Sorry, I said that backwards when I said it. So remember, all of the false implies anything is true, because what I was getting at is if I say, if it's raining, I will drive you home, even if it's whether or not I drive you home doesn't mean that the statement I told you was false. Like, maybe if it had been raining, I would have driven you home. So even if it's false implies anything, that's still true. So the only thing that's false for an implication, remember, is the true implies false. Sorry about that. So what columns am I looking at? I'm looking at R implies the and column. So we have true implies false gives false. False implies false would give true. True implies true is true. False implies true is true. True implies false is false. False implies false, false. True implies false, false. False implies false, true. Essentially, anything that's not true implies false would give true. All of the true implied falses are false. Questions, concerns on that?
So if false implies false is false?
False implies false is true. So if I said, no, wait, yeah, wait, no, I think no, wait, no, I'm looking at the wrong thing now. Let me just triple check that nope, I highlighted the wrong thing. So I'll say more about that in a second. But false, false, true, 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 false, true. Who? Oh Lord. False implies false is true. True implies true is true. False implies true is true. True implies false is false. False implies false is whoops. True. True implies false is false. False implies false is true. So sorry, so I mixed up that one right here. False implies false is true. If I say, if it's raining, then I'm purple. Well, if it's not raining, then we can't really say anything about whether or not it's true that if it was raining, I'm purple. You know, maybe if it magically started raining, maybe I'd magically turn purple. So false implies false is still considered to be true. So I misdid one of those. So the only thing that's false with implication is true implies false. Sorry about that. Any more questions? Okay. Everyone's favorite thing. So gotta pull up something really quick. I think it should still be in my clipboard. Yes. Everyone's favorite thing. Let's talk about these for a second. Now again, I'm not going to ask you to prove anything from scratch. So something like this, I wouldn't ask you to prove it from scratch, just like I did the first exam or whatever exam this showed up on. I would give you something like this, or something where on the exam it was like the table was filled out, but there was just a couple blanks. So I want to talk about this in a tiny bit more detail, because I definitely feel like this is something that was a struggle for a lot of people. And I think partly it was because of how I explained it when we did it originally. I'm going to run out of space. I didn't leave myself enough space to actually write the answer. Can I move this again? Let's try to move it down there. There we go. So especially with a setup like this, the main thing I suggest is to look for differences in the statement from the statement above to the statement below. Now, sometimes a statement can come from a statement that's not just the one above it, but it's a good starting place. So if we wanted to fill out this table, and so we have our rules right there, we just need to figure out which rule was used in each place. So if we look at the first statement to the second statement, what are some differences that we notice? The things that are different is that there's now a negation in the front, and this implies symbol turned into an or, but then everything else at the back stayed the same. So essentially when I'm looking for what rule that must have come from, the main thing I want to look for is something that deals with an implies to an or and then picks up a negation. So if I start looking through all my rules, the only thing that includes both an implication and an or is this implication statement from the equivalence rules. Everything else either has a implies or and or, sorry, or, and I don't know how else to say that, or and or. But the only one that includes both of them is the implication one. So this must be implication. So let's triple check that it was used correctly. So essentially we have P implies Q can become not P or Q. So essentially would negate the thing in the front and they'll leave the back alone, which is exactly what happened here. We negated the R, but left the back alone, and the implies turned into an or. So since that matches directly, so remember, it doesn't have to match, it doesn't have to be P implies Q. It can be something implies something else. It can be as complicated as you need it to be. So this jump from 1 to 2 is an implication. That's not how you spell implication. And remember, you always refer to which step it was used on. So it was used on statement 1, and we used the implication to get there. And then from step 2 to step 3, let's try to see if step 3 might have come from step 2. Maybe it came from step 1, but again, the best case is just try to think above it. What's the only difference? The only difference is essentially the placement of these parentheses. Everything else stayed the same. No symbols changed, no things got negated. Everything else is the same besides the placement of those parentheses. So if we look over at our rules and look for one that kind of moves parentheses around, and start looking for moved parentheses. The only two that I might be back and forth between, maybe, would be these last two. But if you take a closer look, the distributive changes signs and it doesn't have all the signs being the same to begin with, where the associativity rule has all of the signs being the same and all of these here are ors. And all it does is change the parentheses around. So what must have changed from, what must have been used, I should say, from 2 to 3 must have been associativity. I also should have given y'all a second to write this down. I'm sorry, I forgot that y'all don't have this. I should have given y'all a second to write that down. So I'll pause for a minute in case y'all want to write the rest of that table down really quick. Sorry about that. So that's like a big tip with these is if you're trying to figure out one step to the other, look for differences. Like what changed from one line to the next, and then go over to your rules and see which rules deal with those kinds of changes. So from 3 to 4, if we start looking at some changes here, the back completely stayed the same. So the or Q didn't change at all, but this front piece essentially really changed. We have that the negations by the letters aren't there anymore, and the negation's now in the front. And then the sign flips. Well, that's not really what happened, but you know, it changed from an or to an and. So it changed sign. So we were looking for something that essentially changes the sign in the middle and does a lot of hoopla with the negation. Pulls the negation out, changes the negation on the inside, something like that. So if we start looking at our rules, all of the inference rules are pretty much out. So that doesn't help us at all. So if we look through our equivalence rules for ones that deal with flipping signs and negation. So if I wanted to be really, you know, so let me just pull both of these. Nope, that circle's a little too big. So say you said, well, the distributive looks like it plays around with signs and flipping signs over, so that's why I included that one. But the one that not only involves flipping a sign, but also deals with negation is only the De Morgan's law. And if you think about this, we're kind of doing De Morgan's backwards, if you will, where we're going from the right side to the left, where we're essentially starting with, let me zoom in a little bit. Well, then I can't see that. Well, maybe I'll just try to circle it. So we're dealing with kind of the second version of De Morgan's, where we essentially have not R or not P, and then we pulled the negation out to have the not in the front, and then just regular R and P. So remember, it doesn't have to match up perfectly. That one kind of does besides the letters. But even if it was more complicated than that. So here is from 3 to 4, we did De Morgan's law on 3. And then if we keep going, same idea. What's the difference between 4 and 5? Well, suddenly we've got an extra negation. That front piece essentially stays the same otherwise. The Q stays the same, but then the sign changes from an or to an implies. So we're looking for something that deals with an or and an implies and gets us an extra negation. So if we look at our rules again, the only thing again that deals with an implies and an or is the implication rule. So let's triple check that this is actually what happened here. So we're essentially again going backwards, if you will, where we're essentially starting with a not P or Q, where the not P is the R or P. Sorry, and P. And then the or Q is the or Q. So the P now becomes this kind of big piece, and the Q is still luckily just a Q. So if this tells us that this changes over to P implies Q, that means that we would have, did I write this down wrong? Well, I kind of did. So yeah, I should have jumped it. Derp, 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 herp, derp. Herp, derp. I mean, it's not wrong. Okay, so let me, I just probably should have written it differently. So we change from a not P to a regular old P, which can almost be thought as negating it. I know negating and negative, we're going to use the double negation in a second. But instead of thinking of it as removing the negation, you can think of negating it. So that's why I pull up a negative negation of R and P implies Q. Again, I probably should have written that differently in the statement, but that's my bad. It's still the rule, though. It's still the implication on line 4. It's still changing the sign of the first piece and then leaving the second piece alone and changing the or to an implies. So that one turned out a bit grosser than I thought. But then this last piece from 5 to 6, we take the double negation in the front. And we have a double negation rule. The only thing that deals with a negative negative becoming something else is the double negation rule, which turns it into just a positive, if you will. So a double negation on 5. Does that make any sense? Does anyone need more explanation on that the kind of weird one from 5 to 4, 4 to 5? Or are we okay about that? Okay. Let me just do one thing. I know no one said they needed it, but I'm going to do it anyway. Essentially what's happening is we're essentially, the way you think about it is you think about, instead of going, so blah, blah, blah. I can rewrite the implication rule as P or R goes to not P implies Q. Like I can totally change that around. It's perfectly fine as long as I'm consistent. So the regular P turned into a negative negation of P, and the other one turned into a negation. I said that backwards. The negation turned into a regular, the regular turned into a negation. And kind of that kind of rewrite of the implication rule is kind of what I'm using. Is I'm taking my entire regular old P to be the not R and P, and then I'm negating it when I switch it over to the implies. Maybe that was more confusing than what I said before, but hopefully that makes sense. Questions, concerns on that? So again, biggest tip I can give on this is look for differences. What's the differences between one line and the next? Look for a rule that deals with those types of differences. Okay. What do we got next? I don't even remember. I wrote this like an hour ago and I don't even remember what comes next. All right. Oh, predicate logic. Okay, cool. So let the domain be the set of animals. H of x means that that thing likes honey, and B of X means that thing is a bear. We want to translate these two things into predicate logic. I'll wait like 5 seconds in case some of y'all are writing that down. So maybe I can babble a little bit while I stall. So predicate logic, remember the predicates, why am I writing in purple? Predicate logic are the for all, that's the universal one. And then the there exists, the existential. Also remember that when it comes to translating things, the maybe I shouldn't use an arrow. How do I want to write that then? The for all matches with an implies symbol, usually. Usually if you have to write a statement that involves a for all statement, you're going to have an implies. If it has more than one piece to it. And then the there exists usually matches with an, why am I blanking? With an or. Matches with an or. No. With an and. I'm sorry, I was right the first time in my head. Matches with an and. So say we want to translate at least one animal likes honey. So essentially there exists an animal that likes honey. So this doesn't have to do anything with the bear piece here. So that's what I mean by like two pieces. We aren't going to actually need the and symbol here because we're not using more than one thing. We're just using the likes honey piece. So all we need to say is there exists some animal X. So I know I said that, but then I only wrote the predicate logic. So there exists an animal X, because remember the X is essentially saying an animal that likes honey. So just there exists an X, H of X. That's all it would be for that one. There exists some animal that likes honey. Whereas in the next one, every bear likes honey, that's going to involve both of those. So we're going to need an imply, well, I just gave it away. We're going to need an imply symbol here because we're going to use the for all, because if it's every bear, it's all bears. So all bears like honey. Now, this is where it gets a bit weird, where in predicate logic, it almost doesn't sound like that. Like you feel like you should be able to write every bear likes honey in some kind of predicate logic, but it actually becomes for all bears, if it's a bear, then it likes honey, which is why, again, that matches kind of with an imply symbol. So we're going to say for every animal X, if it's a bear, so B of X, then it likes honey, H of X. So for all animals X, if it's a bear, then it likes honey, gets the point across that every bear likes honey. Because this takes into consideration bear, then it likes honey. That make sense? Okay. Let me add in one more kind of over here really quick. If I wanted to say something like there is a bear that likes honey. So I wanted to add in an extra one really quick. So there is a bear means that there's at least one. There could be more than one bear. It could actually be all bears, but this is just saying there's at least one bear that likes honey. This would be an exists, but then it's essentially if it's a bear and, sorry, I shouldn't have said if. It's a bear and it likes honey. So there exists at least one thing such that it's a bear and it likes honey. And again, that's kind of why we say exists matches with and. All right, we end at 2:30. Okay, so again, we'll just keep going as far as we get. I don't think we'll get through everything that I have written down here, but we'll just see where we get. So this next one has to do with sets. I forgot to format that better. I'll write it out in a second. So essentially we have 100 people, 100, sorry, 100, I can't read. 150 people at a Van Halen concert were asked if they knew how to play piano, drums, and guitar. So we have 18 people could play none. So I meant to format it like this, but I forgot. 10 people can play all three. 77 people could play drums or guitar, but not piano. 73 people said that they could play, 73 people could play guitar. 49 people could play at least two. 13 people said they could play piano and guitar, but not drums. 21 people said they could play piano and drums. And we want to complete essentially draw a diagram, a Venn diagram, to essentially represent all of that material, and then figure out how many people only play guitar. So let me zoom out a tiny bit if it'll let me. Why is this? There we go. And I'll keep all of that information in. And let me just, so I'm going to draw a box first. And so remember that essentially we're talking about 150 people, but some people don't play any of them, so we need to put them somewhere. But then we'll have, you know, essentially a 3-circle Venn diagram. That's not going to be large enough. I need to draw this larger. I want to leave space for work, so maybe I'll do this. There we go. Whoosh, whoosh, whoosh. Sure. That works. Let's call this one our guitar circle, this one our piano, and this one our drums. And then the entire thing is everyone. So I'll hold on a couple seconds in case people are still writing stuff down. So this is kind of using that inclusive exclusion principle that we learned in sets, but a bit, what's the word I want? Like a step up, like the one we stated, it essentially said that the cardinality of the union of two sets is the cardinality of the first plus the cardinality of the second minus the cardinality of the intersection. This question is kind of using that, but to a higher degree since we have 3 instead of 2. But we can also just kind of logic it out. So let's try to figure out where these numbers and how these numbers play into this diagram. So the first thing is that 18 people play none of these instruments. So there's essentially going to be 18 people just chilling on the outside of those 3 circles, not in one of those circles at all. And then we're told that 10 people play all 3 instruments. So where does that turn out on our diagram? That's going to turn where they intersect in all 3 circles. So this kind of inner piece here is going to have 10 people in it because 10 people play all 3 instruments. And now it gets a bit more complicated. So where do I want to start here? Let me first start by saying we start out with 150 people, and there's 18 people who don't play any of these. So if we think about that, there's 132 people essentially in the Venn diagram. So I'll be referring to this 132 a lot when I'm doing some of these calculations. So there's 132 people who should be considered just in the Venn diagram itself. So the first thing is let's kind of consider what these other pieces are telling us. So plays drums or guitar, but not piano. So this 77 would be essentially the guitar or drums, but not piano. So those 77 people could end up anywhere between, you know, just guitar, just drums, or both. 73 people play guitar, I don't know how to do this in case people are colorblind. Let's do a little whoosh whoosh. So the guitar, maybe I'll do just 1, 2, 3, 4, and then I'll just loop around. Guitar could be essentially both, either just the guitar or both guitar and drums. And then what else do we've got? We've got 49 people play at least 2. That's too hard to put out there. 13 people play piano and guitar, but not drums. So let's put that on there somewhere. Piano and guitar, but not drums. Let's put a little circle in there. Where am I? Piano or guitar, but not drums. Oh, no, I'm sorry. I read that wrong. This one can already go on there. And that's because the difference between the two phrasings, this one says drums or guitar, this one says piano and guitar. So since they play piano and guitar, but not drums, that actually ends them up in just this middle piece between guitar and piano. So there's 13 people who land in that sliver there.
With the 73 people that play guitar, does it say that they just play guitar?
I didn't mean to do that. I actually drew that a little dorky. Sorry, I actually drew that incorrectly. Let me also make this a little larger. But no, it's not saying that they only play guitar. It says that they play guitar in general. So actually it could be anywhere in that guitar circle at all. They could be just guitar, they could play guitar and piano, they could play guitar and drums, they could play guitar, piano, and drums. It's not just saying they only play guitar. So the only way that they could specify that they only play guitar is if they literally say they only play guitar.
Okay.
But since they play guitar, they can play guitar with any other instrument, maybe none of them. So first thing I want to try to do is, so I did this earlier and now I'm like blowing my mind for some reason. Where did that come from? Oh, play piano and drums. Oh, yes. Okay. I'm so sorry. I understand now. This 21, play piano and drums. Now that doesn't say that they can't play guitar. So that's going to end up in this piece here. They play piano and drums, and possibly guitar. They have to, whenever you read questions like this, they have to be very specific in their phrasing. So this doesn't say and not guitar at the end of that statement. So they also could play guitar. So essentially there's 21 people in that entire sliver, but there's 10 people in the middle. So the amount of people only in the piano and drums, but not guitar, would only be 11 people. Does that make sense? So there's 21 people who play piano and drums and maybe guitar. And since there's 10 people who also play guitar in that group, there's only 11 people who only play piano and drums. Now that we filled out those 3, this is where it gets a bit more complicated. Well, it was already semi-complicated. I don't want to phrase that poorly. But now we essentially do a bit more math here. So let's try to figure out how many people only play piano, because that's kind of the only one that we don't have as much. That's the one that we know the most about. We know the most about the piano piece here. So if we want to figure out how many people play piano, well, there's 132 people in the entire Venn diagram. And we know that there's going to be, well, we have to take out this 13, the 10, and the 11 because they can't end up in here. They can't be in both places. So that's going to give us 98. And then we essentially know that blue circle, essentially everything else that's the guitar and drums, but not piano, is 77 people. So we take out those 77 people. There's 21 people left, which means there must be 21 people who only play piano. Because what I've done is I've taken out the people who play piano and other things in the 13, 10, 11. And I've taken out the people who don't play piano at all in the 77, which means that I only have 21 people left to play piano, and only piano. What do I want to do now? What I want to do now is, I think the drums is the next piece that can be figured out nicely. Oh, yeah. So say I want to focus now on figuring out how many people only play drums. Well, essentially, I need to know how many people play guitar or play guitar and drums and take that out, right? So if we think about this guitar piece here, so we know that there's 73 people who play guitar. So like the amount of people who play guitar is 73 people. So that entire guitar circle must encompass 73 people. We already know that 23 are spoken for in the 13 piece between guitar and piano and the 10 piece in the middle. So we know that 73 minus 13 minus 10 equals 50 is just guitar or guitar and drums, right? So there's 50 people who play only guitar or guitar and drums. So I know this is a lot of math. So if I want to figure out how many people are only in drums, I know how many people are in all of the piano pieces, and I know how many people we just found out how many people are in either of these two. There are 50 in either guitar or guitar and drums. So if we take the total amount of people in this Venn diagram, minus all of the piano hoopla, the piano and the multiple pieces hoopla, minus the 50 people who must be either just guitar or just drums. Sorry, just guitar or guitar and drums. Leaves us with 27 people who only play drums. That make sense? Or have I lost people in the sauce? Now we're almost done. Because now we only have these two pieces that we know must have 50 between the two of them. So how do we figure out how many people are in either of those pieces? So I didn't mean to scroll down. I need a piece up here. So let's look back at the information that we have. So we already used that 18 play none of them, 10 play all three. We've been using the 77 and the 73, and we placed the 13 and the 21. We haven't used that 49 at all. Okay, so we haven't used that 49 plays at least two. So that means that essentially all of these pieces that are in an overlap, either just between two of them or that piece in the middle, must all add up to 49. So we can find this piece for the guitar and drums piece by taking the 49 and subtracting the 13, 10, and 11. So we know that 49 people must play at least two. We know 13 play guitar and piano, 11 play piano and drums, and 10 play all three, which leaves 15 people that must play at least two instruments but haven't been put anywhere, which means that they must be in the guitar and drums piece. If there had to be 50 people between guitar and drums, 50 minus 15 is 35. So there's 35 people who just play guitar. Questions, concerns about that? A lot to think about in that question. So again, if you're ever presented with a question like this, know that their phrasing has to be specific. So like Ryan asked with the play guitar, does that mean that they just play guitar? No. When it says play piano and drums, it doesn't say anything about guitar, so they could play guitar, they could not play guitar. If they want to be, they have to be specific here. So that's why with the 77, they had to say drum or guitar and not piano. Because without saying the not piano, we can't assume that they don't play piano. So they have to be very specific in statements like this. So if they're not specific, you assume that it's the more general option. So when it says just play guitar, you don't assume that it's for the very only play guitar. You assume it's the general play guitar in some fashion. And then it's just a hope your brain can keep track of all of the numbers. Okay. I'm not seeing any questions on that one. What's next? A nicer set question. So we've got a little less than 15 minutes left. Would y'all rather me do the induction one instead? Or no? Raise your hand if you'd rather the induction. Yes? Okay. Okay, cool. We'll do the induction one. I'll write the answers out for all of the rest of the ones that we don't go over. But since induction was another one of those ones that trip people up a lot, let's go ahead and do that one. So prove by induction that the sum from 1 to n of 5i is equal to 5n times n plus 1 over 2. So, as always, base case first. So that's when we let n be 1. So everywhere we see an n, we're going to put a 1. So everything's going to stay the same except everywhere I see an n, I'm going to put a 1. I should probably put a question mark above this to say that I'm not saying it's true yet. I have to make sure it's true. So that left side is essentially saying the sum from 1 to 1, so we just have one term, of 5i. So essentially we're letting I be 1. So we're going to get 5 on that side. And then we're going to have 5 times 2 over 2. So the 2's are going to cancel out. We're going to get 5 equals 5. So our base case is set. For the sake of space, I'm going to write my inductive hypothesis on the right here. So this is where you assume that, assume true for n equals k minus 1. So essentially everywhere you see an n, you now write a k minus 1, and you essentially just say, assume this is true. So assume, I can probably fit that all here. So everything stays the same except n's become k minus 1's. And assume it's true. There's this thing in my way. Let me clean that right side up a little bit. 5k minus 1, k minus 1 plus 1 over 2. You could simplify that right side a little bit, and I will in a minute, but for the sake of writing it down, you can just write it down in its full generality without really simplifying it at all. So we're just assuming that that's true. And then, of course, the meat and potatoes is the inductive step. And that's where you show it's true. That doesn't look like true. For n equals k. So if it helps you, write out what you want first. You don't have to write it out, but if it helps you figure out how to start. So we essentially want to take that entire thing, leave everything alone, but everywhere we see an n, we're going to put a k. Nope. Everywhere we see an n, we're going to put a k. And you pretty much start with the left. And I'm going to put quote unquote, find the right. You essentially want to work with the left-hand side, kind of forget about the right-hand side for a minute, and just manipulate the left-hand side until you get the right-hand side. And the left and right-hand side that I'm talking about is this thing that I want. So I'm going to start with the left-hand side. I'm going to start with that sum piece, and I'm going to manipulate it until I get that right side. But I'm going to kind of forget about the right side for a second while I do that. So essentially, we're going to start with the left side. The thing I'm about to write to the right of this is unnecessary. The things you would, the things you would actually want are going to be what I'm going to write below it. So this is optional and this is needed. But if it helps you remember how this goes, what that sum is actually saying is essentially plug in 1, then add what you get when you plug in 2, then keep going until you hit k. Well, if you hit k, the thing you must have had before it must have been k minus 1. So if it helps you to write that out, you can. But essentially the point is that this piece up to the k minus 1 is the thing in the inductive hypothesis, because I can rewrite that. So you would want to write this. You would want to write the sum from I equals 1 to k minus 1 of 5I plus 5k. And maybe so I shouldn't make that let me just underline it. So essentially that first chunk becomes this, I don't want to say new, but you essentially just split it up. So if it's the sum from 1 to k, then it must have included the sum from k minus 1, and then we just kind of tack on that kth term at the end, because we still need it. And then the point is that k minus 1 thing in the inductive hypothesis is equal to something else. So we say that that's equal to our 5 k minus 1 plus 1 over 2 plus 5k. We replace that k minus 1 sum with the inductive hypothesis, with the thing we assumed it was equal to in the inductive hypothesis. So you start with the left side. You essentially create the inductive hypothesis within it. So essentially, since we started with the sum from 1 to k, we know what the sum from 1 to k minus 1 is. So we break it up into the sum from 1 to k minus 1. And then since it was originally the sum from 1 to k, we still need that kth term at the end. Once you replace, that's when it becomes the algebra game. And you essentially want to manipulate that to try to get the right side. So now you kind of put the right side back into your brain and try to take what you now have and make it look like the right side that you wanted. So we want this to somehow form a 5k times k plus 1 divided by 2. So let's try to do our algebra game on this and see if we can get that. First thing I'm going to do is I'm going to simplify this fraction a little bit. So I'm going to do 5k minus 5. I'm going to distribute that 5 through, and then let me simplify this back piece. The the 1's essentially cancel each other out, and you just get k. Then I'll distribute that k through. So 5k squared minus 5k over 2. And now I got to try to smush those together. Well, I can't add those together unless I have a common denominator. You can't push something that's a fraction in with something that's not a fraction. So I need to essentially turn this 5k into a fraction. And I want the denominator to be 2. So essentially the first term stays. And then if I want this to be over 2, well, essentially I started with 5k over 1. So if I want to change that into over 2, I multiplied the denominator by 2. So I have to multiply the numerator by 2. So I'll get 10k. Now that they have a common denominator, I can smush them together. Smush, smush, smush. I'm running out of space here. We're almost done though. So 5k squared minus 5k plus 10k over 2. That negative 5k plus 10k can get, smushed together to get plus 5k divided by 2. Now let's remind ourselves what we were looking for, because we've done a little bit of algebra, we've reduced a lot. So let's check and kind of look at our progress. Well, what we want is we want 5k times k plus 1 over 2. So we've got the over 2, that looks pretty good. Can I somehow turn this into a 5k times k plus 1? The answer is yes, if I just factor out a 5k from the numerator. So notice that both of those terms in the numerator have a 5k in it. So I can pull that out. What am I left with in the first term if I pull out a 5k? I'm left with a k. I'm left with quote unquote nothing if I pull out a 5k from the second piece, but we kind of need that placeholder of 1 divided by 2. And hey, look, I found a 5k, k plus 1 over 2, which is exactly what I wanted, and I'm done. I don't have enough space to write the, well, I guess I can write it over here. Therefore, by induction. By induction. And then you just essentially go back to the thing that it originally said. So it originally was in terms of ends. So to clarify one last time with this inductive step, you start with the left side of what you want. You want to essentially plug K in everywhere you see an N. And you want to eventually get out to the right-hand side if you were to replace every N with a K. And there's all this hoopla in the middle, but essentially we want to get that these two things are equal to each other, and with enough hoopla, we can. And the way we can do that is by using the inductive hypothesis to replace into our inductive step, if that makes any sense. All right, questions, concerns about that? Okay, so there were a couple more things on here. We hit most of it. There was that set one we were about to do, some things with one-to-one and some sequence stuff, but then I was done. Obviously, there's way more stuff that was covered in this semester, but I was just trying to get a class worth of material from some of the earlier stuff. So I'll fill out the answers for these other pieces and I'll post it on Blackboard. Your kind of official review got put up on Blackboard yesterday. Let me triple check that it's there. Yes, it is. So there's a final exam review in the exam folder, like usual. It's a little long, but that's because there's a lot of material. But of course, you don't have to do all of it if you don't want to. So if you just want to jump around to the pieces that look like you might need to practice it, I'll be getting the answers up when I get a chance. I'm focusing on my 122 today, so it'll probably be tomorrow by the time I get the answers up for those. I think I also need to put up exam 3 answers, but I'll need to wait till the end of the week to do that. So by the end of the week, you'll have the exam 3 answers up. If you want your exam 3 back, just like shoot me an email and I can scan it to you. Otherwise, exam 1 answers are up, exam 2 answers are up. Good. So yeah, I'll get the final exam review answers up as soon as possible, probably tomorrow, worst case scenario Thursday. Remember, you have homework that's due on Thursday. Thursday is when your homework is due, that last homework. Final exam is next Thursday. I'll be putting the office hour stuff on Blackboard. I don't think there's anything else I need to say. No, I don't think there is. So otherwise, if I don't see you for questions or anything like that, I won't see you ever again. Well, maybe not. But anyway, otherwise, study well. Let me know if you have any questions, and I hope your finals week goes well and as least stressful as possible. And I hope the rest of your semester goes well. Otherwise, if you have questions, feel free to stick around. Otherwise, have a great day, and bye.